I have to find the acceleration in order to do the second part. The trick to doing number 13 to find the acceleration, don't treat that as a 2 and a 12. Treat it as 114. And if you treat it as 114 kilogram mass, I would argue, hey, now it's the same as this question right here, but not even any friction. Even better. Okay? The real question is, okay, how would I find the coefficient of friction between the 2 kilogram mass and the 12? Is there one? Well, I would argue, supposing right here was ice, and you suddenly dropped this down, isn't it possible, in fact, wouldn't it actually be likely that that 12 would yank out right from underneath the 2 and the 2 would drop down? You've done it sometimes with like books or stacks of magazines. You've given a quick yank and everything else has dropped down. If you do it quick enough, if the coefficient of friction is small enough, you can get away with it. In fact, that's how magicians yank a tablecloth out from underneath the table. Who was in my Physics 11 last year? We did I'm sure we did a bucket or a little container of water and somebody laying underneath it. And we yanked the paper towel out, right? Yes. So I would argue there must be friction there. Otherwise, that 2 wouldn't be traveling with it. Okay. Let's draw the free body diagram just on this 2 kilogram force. What are the forces acting on it? Get the obvious ones. Darn right. By the way, the other reason I say that, doesn't it feel good to know that you can get at least part of this without thinking too much? I can draw gravity, I can draw normal force, and you've got your brain flowing, right? So gravity, is it sinking into the ground? No. Is it lifting into the air? No. So I'm pretty sure there's a normal force. Which way is that 2 accelerating? Look at the picture. Yeah, to the right. So there must be a force to the right. Which force is accelerating it to the right? The applied force isn't touching it because the rope isn't touching it. Cole. Friction is. Must be, because that's why if it was ice, there would be no net force and it would stay where it was. Friction is what's pushing this thing to the right. I think it's that. And again, the big temptation is people want friction to be to the left. Not in this case. I don't think so. I know it's accelerating to the right. I know there has to be a force there. It can't be tension. You know how I know it can't be tension? Rope's not touching it. Can't be an applied force. You know how I know? Because the rope's not touching it. What's touching it? Well, that 12 kilogram friction between the 2 surfaces. Who's losing? There isn't one. Who's winning? Winner equals, and since we're only looking at one mass, Brett, it's going to be M1 times A. Friction is what times what? Mu times the normal force. Oh, I don't know the normal force, but look. I know another force the same size as the normal force. What? Okay, so I can say mu M1G equals M1A. Conveniently, Brett, I notice, oh, look at that. The masses cancel. I like. How would I get, because they wanted me to find the coefficient of friction, how would I get the mu by itself? Do I know G? Yes, 9.8. Which A? That's the acceleration of the overall system. That's why I had to find that 3.6 meters per second squared first. It's going to be 3.6 divided by 9.8. That's the minimum coefficient of friction. And by the way, it should really say the minimum coefficient of friction, because it could be stickier and we got no problem. But it's got to be at least that sticky, at least. Otherwise, that 12 is going to slide out from underneath and that 2 is just going to drop down. Is that okay? Yeah. And now that you see that, you're like, oh, didn't really do anything new there. I had to think about the free body. Yes? Oh, could I show how to find 8? Sure. It's going to be, I'm going to call this one big M1. So it's going to be M1G, normal force number 1, no friction. Yay! M2G, tension. Who's winning? No, not I guess. I know. Is there any force in this direction at all? So can it possibly be moving to the left or accelerating to the left at all? So scene one, who's winning? You know what? If you drop something over a cliff, I think it's going to pull stuff over the cliff with it if it's on ice. Are we on ice? Yeah. Okay. If you're standing on ice and you throw a big weight over a cliff, I guarantee it's going to pull you over the cliff. So who's winning? Not I guess, for sure. M2G, absolutely. So it's going to be winner minus tension plus tension. Are there any other forces along this path? No. You know what? That M1G doesn't show up. That normal force number doesn't show up. Not, you know why? Because there's no friction. It's going to be equals, and it's going to be M1 plus M2 plus M3A. Take it from there? Yeah. Yep. Common mistake. Kids they really, really want this to appear somewhere in the equation. No. No. Well, it sort of does. It appears over here. These two masses do provide inertia and slow that 8 down because the 8's not in free fall. There's a rope. Any others? Okay, let's continue on then. I don't know if we're going to get through the whole lesson, and there is an assembly today for my block A's, so if we don't get through the whole lesson with you. Lesson 5, the Atwood machine. Again, this is mostly Physics 11 review, but we're going to build and add. The Atwood machine is a pulley system as seen below. It's a nice visual representation of some good force questions. So what we're talking about in the Atwood machine is something like this. When one goes up, the other goes down. When one goes up, the other goes down. It's a counterweight system. This weight can be called the counterweight. Elevators work like this. Elevators don't actually lift you and the whole car. They only lift you. They have a weight exactly equal to the weight of the car on another pulley somewhere, and that way it's a fairly neutral weight. They're only having to work to lift the mass of the people in the elevator. So here's my first question for you to think about. Suppose I put equal masses on both sides of an Atwood machine. Now, once again, Nico, I'm teaching you garbage. Our Atwood machine is magical. Do you know how much mass the pulley has? None. You know how much friction the pulley has? None. You know how much mass the ropes have? None. You know how friction the ropes have? None. So but it's a good analogy, Emily, for us to think things through. So supposing equal masses are placed on both sides of an Atwood machine. So imagine this, except imagine a frictionless pulley. This pulley is not frictionless at all. And so I have equal masses, and supposing I lift one of the masses up and then let go. When released, how does the system move? A, the system remains at rest. B, the higher mass falls. C, the higher mass goes higher. And convince me. Oh, this is an opportunity for us to vote. Let's see. So we have equal masses. Who says A, it remains at rest? 1, 2, 3, 4, 5, 6, 7, 8. Who says B, the higher mass falls? Explains a lot about him. Who says C, the higher mass goes higher? Convince me. This is the first time, by the way, that C, I think this is the first time I've ever had a class have C be the winner, which is interesting. Doesn't mean it's right or wrong, I'm just saying it's... You know what? This looks like a job for a good free body diagram. Let's do that. Let's call this M, and since they're the same mass, let's call that mass M, because it does say they're the same mass, yes? So I don't need to worry about M1 and M2. What are the forces acting on the left-hand mass? Get the obvious ones. Is it in free fall? No? Oh, there's a rope. What are the forces acting on the right-hand mass? Get the obvious one. Also M1G. Is it in free fall? There's a rope. Who's winning? I'm not sure. Well, you guys seem to feel that if this higher mass goes higher, I guess this mass, the right-hand mass, must be somehow winning. That's the majority. Let's try that. So it would be winner, and then we run into tension, so that's minus loser. Now, this tension here ends up becoming a winner when it goes all the way around, right? It ends up pointing down on the other side. Yes, 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 yes. So it's going to be a winner. And this gravity here, let's see, it ends up pointing up over on this side, yes, when I work it all the way around? So it ends up being a loser. And that equals the mass of both times A. Oh, what is the left hand? Thanks, just put it face down. What does the left hand, in the appropriate block, thanks Dylan, what does the left hand work out to, the left hand side? Are the masses 0? No. So if this works out to 0, what number must be 0? Nathaniel. Or it could be moving at a constant speed, but the question clearly says we start from rest and then release. So if we're starting from rest and your acceleration is 0, you better stay at rest. Thank you. Answer A. Acceleration is 0, therefore A is the correct answer. Okay. Example 2. Now we have unequal masses. Mass 2 is 5.8, mass 1 is 2.3. Solve for the acceleration and find the tension. You know what? This looks like a job for a free body diagram. Except I'm not going to redraw everything. I'm going to label the forces. Miller, what are the forces acting on mass 1? Get the obvious one. Austin. I said Miller. Good gosh. Austin, what are the forces? Because I teach your brother in the other class. You know, and it was funny. He sits right back there too. Eh? Sorry? M1G? What else? Don't walk over there. We're still on this mass here. There has to be, because otherwise it would be in free fall, and I know it's not. What are the forces acting on mass 2? Get the obvious one. Yeah, so obvious you wanted to jump over there. Not yet. And what else? Tension. Who's winning? This is where you have to do some physics. Vlad, I'm sorry. You're going to have to clue in the heavier mass is winning. Just like ice is slippery when you're going over a cliff. Which one's the heavier mass, Vlad?
Mass 2.
So we're going to go winner. Tension is a loser. Oh, but the left-hand tension, can you see when I come all the way around, it ends up pointing downwards. It ends up pointing as a winner. And M2G, although at first you might think it's a winner because it's down, M1G, at first you think it's a winner because it's pointing down. Follow it all the way around. When it gets to this side, which way does it end up pointing? Up, right? Right? No, yes? Yeah. So it ends up being a loser. And that equals M1 plus M2 times A. Why am I stretching, smiling, and chilling? Tension cancels. I like that. I'm losing some tension. Ah, good stuff. Okay. Part A said find A. How would I get the acceleration by itself? Oh, that's not too bad. Acceleration is going to be m2g minus m1g, all divided by m1 plus m2. It's going to be 5.8 times 9.8 minus 2.3 times 9.8 divided by 5.8 plus 2.3. I encourage you all, try this on your calculator, see if you know how to type this in. Let's see. It's going to be 5.8 times 9.8 minus 2.3 times 9.8. I got more than one number on the top, so I better put that whole mess in brackets. Divided by bracket. 5.8 plus 2.3. Do you get 4.2345679? No? Yes? So 4.23? There's part A. What does B want me to find? Tension. Look at one mass. Which mass? Really doesn't matter, although I'm going to be clever. When in doubt, I like to pick the mass in which tension is the winner, because the equation is a tiny bit easier. Which one is tension winning in? Mass 1. So let's go, because mass 1 is moving up, which means tension must be the winner. Why is mass 1 moving up, Vlad? Because a heavier object will pull a lighter object. Okay. Winner minus loser, shut up, Mr. Duke, sorry, equals M1A. Do you see why I picked that one? Because to get the T by itself, I get to plus something over, and I make less mistakes plussing things over than I do minusing things over. I'm pretty sure that tension is going to be M1A plus M1G. What was mass 1? 2.3. What was A? I'll write 4.23, but I'll use the value that's on my calculator. Plus 2.3 times 9.8. $32.3? 32.3 what? Newtons. And I would get the same answer if I did mass 2. My equation would be different. It would be M2G minus tension equals M2A. I'd have to rearrange it a bit, but I would get the same answer. All right. A little trickier now. Consider the following system. Now instead of pulling on something, we're pushing on something. Okay. Which of the following is the best force diagram for mass M2? A, B, C? I'm really tempted to vote, but let's see if we can just figure this out together. You know what this looks like a job for? A good free body diagram. And this is complicated enough that I think I will redraw it. So I'm going to say to myself, self, here's mass 2. What are the forces acting on it? Get the obvious ones. I know there's some weird stuff. I'll deal with that last. Get the obvious ones. Darn right. Is it sinking into the ground? Is it lifting into the air? And I'll call that normal force number 2 because it's mass number 2. What else? Now, see this force right here? What force is the applied, what mass is the applied force touching? Mass 1, mass 2, or both? Mass 1 only. Which means that applied force is not what's pushing mass 2. Okay. Which way is mass 2 going to accelerate? So there does have to be a force this way. Which force? It's the force of the wall of mass 1 pushing against the wall of mass 2. You could call it a normal force because it's a surface pushing against a surface, but I'm going to give it actually a new name. I'm going to call it a contact force. That's what's pushing mass 2. Mass 2 is getting pushed by a contact force. Mass 1 is getting pushed by the applied force. So mass 1 is exerting a contact force on mass 2. Oh, by the way, what's mass 2 exerting on mass 1 then? Contact force in the opposite direction. Newton forces come in pairs. I'm not labeling that on my free body because that's not a force on mass 2, that's a force on mass 1, and I didn't say draw the free body diagram on mass 1. Okay. So now that we've done that, what is the correct diagram? It says explain your answer. There. I did a good free body. I'd take that. What's the most common answer? A lot of kids want to pick B. Well, the applied force should be on there too, Mr. Duke. No, it's not touch. If the applied force isn't touching mass 2, then I'm telling you, don't you put it on mass 2. It's not there. Something's pushing mass 2 to the right, but it's not the applied force. The applied force is pushing mass 1. Mass 1 is what's pushing mass 2. We'll call that a contact force because we have two surfaces in contact. So, welcome to Physics 12. Example 4 says, find the acceleration of the system and find the contact force between the two blocks. You know what this looks like a job for? Free body diagram. Now, let's see. I'm going to see if we can just label the forces. So I have this guy. If we want to give it a name, we could call it F applied, but I'll call it F applied number 1 because can you see, Nico, there's another applied force over on the right-hand side that I'll have to deal with later. What are the other forces acting on the 6 kilogram mass? Darn right. I'll call that M1G. What else? I'll call that normal force number 1. What else? Is it pushing against mass 2? Yeah. Then what's mass 2 doing back to it? So, I think we could safely say, folks, then, that there is a contact force this way. I'll call it F. You know what? I think I can call it FC because I haven't used C as an abbreviation for anything else yet, have I? Those are the 4 forces acting on the left-hand mass. What are the forces acting on the right-hand mass? The 8.25. Get the obvious ones. M2G. I don't know. I'm going to get the obvious ones. FN. Come on, pen. Try this again. Come on. What else? Oh, there's an applied. I'll call it FAP2. And Cole, what did you ask now that I have your attention span back? I think so. So let's go FC. Are they the same FC? Convince me. Forces come in what? Have to be. Mass 1 pushes against mass 2. Mass 2 pushes back exactly the same against mass 1. They have to be. It's Newton's third law. You're looking at a whole different no. Look specifically between those two surfaces. If I touch you, you touch me back. If I push you, you push me back. And it's the same force. Don't overcomplicate it. The diagram, I totally agree, is more complicated. Don't let you trick you out of your first principles, your Newton's 3 laws. If you had to guess who's winning, which way do you think this is going to accelerate? Oh, is there friction? So it is going to accelerate because we're on ice. Who's winning? Yeah, I think the 42.5. So we're going to let that be winner to the right, to the left be loser, and let's walk down all the horizontal forces because we notice, Courtney, the vertical forces are all in equilibrium. So it's going to be winner. Then I run into contact force, but it's pointing to the left, so it's a loser. Then I run into contact force, but it's pointing to the right, so it's a winner. Then I run into 6.75, but it's pointing to the left, so it's a loser. Have I gotten all of the horizontal forces? Yep. What's it going to be equal to? Don't say MA, because it's not. No, I think you're, and maybe I confused you. If you just said MA, I would say no, because, more than one mass, right? Right. We're doing the multi-mass approach. Cole, what do you notice happens to the contact forces? fact, isn't this actually behaving an awful lot like tension did? Yeah. Tension was easier for you to visualize, though, because all of you know if you tug on one end of the rope, the other end gets tugged with the same amount. You really had to think about it for pushing, though. Some of you were saying, no, they can't be the same. So, yeah, they are. If you push on something, it pushes back, same size. And now, suddenly, this really complicated, scary-looking diagram, I'm going to argue now, is fairly easy Physics 12. We lose contact. How would I get the A by itself? It's going to be 42.5 minus 6.75 divided by both masses. You know what? I can even add those masses in my head. 14.25. What's the acceleration? Sorry? 2.51? Anyone else? So there's the acceleration. That's not all they wanted us to find, though. What else did they want us to find? Contact force. Oh, I can do that. I'll look at one mass. And you know what? I'm going to be clever. I'll pick the one where the contact force is the winner, because it'll give me a nicer equation. In which one is the contact force the winner? The left mass or the right mass? The right. So let's go to the right-hand mass, the 8.25. Who's winning? Contact force. Who's losing? The 6.75. And I think those are the only horizontal forces on that. And we're looking at one mass, so it's going to be 8.25 times A. Holy smokes, this falls apart. Joe, how would I get the contact force by itself? So you're saying the contact force is going to be 8.25 times, what was A? Oh, we figured it out. 2.51 plus 6.75. Ta-da! What is the contact force between the two blocks?
27.5 newtons.
Sorry?
27.5 newtons.
Anyone else?
Yep.
The left block pushes to the right with 27.5. The right block pushes to the left with 27.5. And you end up with a net unbalanced force moving sideways when you look at all of the forces. How much more am I going to get? Am I going to get through the whole lesson today, Mr. Duick? Pretty close. We'll see. Example 5. A curling rock, rock number 1, is traveling east across a sheet of frictionless ice. So this ice is perfect ice. Most ice has some friction. This has none. It bumps another rock and it experiences a force that acts briefly to the north. What will be the path of rock 1 after the bump? So it's traveling along and it gets bumped by a rock that hits it, donk, like that. Will it, now I think this is supposed to be an arrow pointing straight, oh sorry, no. My diagram went wonky. Will it move either straight up, straight right, in a curvy path, or do you guys have a little arrow right there? Mine vanished. I don't know if you guys still do. After the collision, assuming the rocks are no longer in contact with each other, what do you think is right, A, B, C, or D? Zach says D. He blurts it out. He doesn't believe in democracy. He believes in dictatorship. Convince me.
I guess since it goes briefly north, then since the force is no longer acting on it,
If there's no net force on it, what does Newton's first law say? It's going to travel how? Straight line, steady speed. Because remember, acceleration, you can do it. You can change an acceleration two ways. You can change the velocity. How can you change the velocity? The magnitude. Or you can also change, what do all vectors have? Magnitude and? You can also change the direction. So C can't be right because it might be going at the same speed, but can you see its direction is changing? That must mean there's an unbalanced force on it. B can't be right because this would be, there has been an unbalanced force on it. There has to be some kind of an acceleration. That hasn't changed its velocity, magnitude, or direction at all. I don't think A is right. I think by a process of elimination, D. It's Newton's first law. And the last one. I think this is the last one, just about. A water bottle is drilled with many small holes so that it leaks when filled. If the bottle is filled and then dropped, what happens as it falls? A, while it's falling, the water stops leaking out. B, the water leaks out at the same rate. C, the water leaks out at a slower rate. Or D, the water leaks out faster. I want you over here to put a little box in your notes, and I want you to write what you think the correct answer is. A, B, C, or D. So we're going to drop a water bottle with some water, and we're going to ask, what's happening here? Will the water, A, stop leaking out, B, leak out at the same rate, C, leak out slower, or D, leak out faster? Let's assume that there is a way, let's call her open. This sounds like a good idea. So we've just tried this lovely experiment. What was the correct answer?
A.
How many of you picked A? Why is A right? That's the real question. Why should you have been able to predict that A was the correct answer? Convince me. Oh, are you saying if you drew a free body diagram on the bottle, what are the forces acting on the bottle? Get the obvious one. And if we ignore air resistance, that's it. And if you drew a free body diagram on the water inside the bottle, what are the forces acting on the water inside the bottle? Get the obvious one. And if we ignore air resistance or the slight tiny amount of pressure from the wall, I think that's it. So could I have done that same experiment with an ice cream bucket with no lid? Yeah. Yeah. Now, a lot of you, though, when I threw it up, you wanted to change your answer, even after seeing when I dropped it what happened. When I throw it up, on the way up, as soon as it leaves my hand, what are the forces acting on the bottle? Get the obvious one. Anything else? No. I gave it an initial force with my hand, but Brett, once it left my hand, yes, it's traveling up, but which way is it accelerating? Which way are the forces? Down. In fact, it's the same mathematical question as when I dropped it. The only thing that I changed was I gave it a positive initial velocity. When I drop it, VI is 0. When I throw it up, VI is positive something. But the equation is going to be the same. So, A. Yes?
Okay, so when it was at rest and you took your finger off the little hole,
Yep.
the air pressure or whatever would make the water pour out.
Well, gravity was making it pull out.
Gravity.
Yep. Okay, what were the forces acting on it? Gravity. It's a little bit more complicated because for water to run out of a small enclosed container, any water that goes out, an air bubble has to be able to get back in to replace it. And that's why it spurts out. Spurt, 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 spurt. It's an old trick. You can, if you have a water bottle or something like that, if you have put a hole in the top lid, you can still close it off. I needed some way to do it without making it messy. But as long as I was willing to allow the bottle and the water to both accelerate at the same rate and free fall, then it won't leak. When I prevented the bottle from accelerating, but I still allowed the water an opportunity to be expected by gravity and accelerate, well, then the water leaked out. Yes?
So if you took that same water bottle and put it in space, the water wouldn't leak out because there's no gravity?
Sure. Yep. Watch. NASA has a terrific YouTube channel, by the way. I'm subscribed to it. Watch. They'll actually have videos of them eating and things, and you can see how tricky it is for them to eat liquids. They have to do them in Ziploc bags, and they have to either suck them out with a straw, or they make the liquid slightly thick enough that they can squeeze it out like Jell-O, and it'll form a spherical ball because of surface tension, and they try and suck it up. It's fun, but tricky for them to eat in space. And some stuff just doesn't work. There's certain things they know, like don't bring potato chips, despite the Simpsons episode where Homer brought the potato. If you see the Simpsons episode where Homer goes into outer space years ago, he opens a bag of potato chips and they go everywhere. That's not unrealistic. That's probably what would happen, and then they're everywhere. They're everywhere, and you don't want to clean that thing, so it's a bit of a mess. Okay? So I wrote here, using principles of physics, explain your answer. I think we've done okay. I would do a free body diagram. We've said the same force acting on both, so they're both going to accelerate at the same rate. They both have the same initial velocity. Okay? I would love to do example 7. It's a wonderful nerdy scholarship one, but I've talked almost all of class. We already did number 1. Number 1, I asked, what if it's thrown upwards? We said the water stops leaking out again. So what's your homework? I think you can try number 2. Take a look at the second question in number 2. What's the first mass? In number 2, the right-hand diagram, what's the first mass? 3m. They don't give you a value. And what's the second mass? M. You can either, if you're a nerd, try doing it algebraically. I think the m's will cancel at some point. Or let the m be 2, which would make the left-hand mass be 6 and the right-hand mass be 2. Or let the m be 5, and the right-hand mass would be 5, left-hand mass would be 3 times 15, if you want to do it with numbers. See if you can handle 3. 3 is fairly nasty. 8. And I'll just give you those ones. I'm giving you the tough ones. I'll talk about those next class if I need to. Do I see you again this week? So I see you guys again Monday. Gives you lots of time to try practicing these, okay?